Welcome to our YouTube channel of series of basic process engineering calculations. In this session, we will focus on the sizing of different sizing scenario of safety valves. The main motto to select this topic is that you will easily get the sizing calculation of orifice, type of orifice, and other details on any website or any handbook. But to size the safety wall, we all know that the basic data requirement is that for which scenario we have to size the safety wall, then what is the required set pressure of that safety wall, and most importantly, what would be the relieving capacity of that safety wall. And that's why I have selected this topic. First, we will discuss about the different scenarios, and as we all know that all the industries or all chemical industries don't have the simulation softwares like Aspen, Aviva, Pro 2 or Promax. So I have prepared the calculation format or the make this session for everyone those don't have the simulation software license, or they can easily design or size the safety wall with the help of this session. So they can calculate the required relieving rate with the help of Excel itself. So before proceeding to actual uh, topic of the session, we will just get to know about the different scenarios which we are using or commonly used in the chemical or pharmaceutical industries. So, first scenario is that of PRV, mechanical PRV, that's pressure reducing wall or pressure reducing stations failure or control wall failure. In traditional plants, you will get the mechanical PRV, and nowadays the trend shifted towards the automation or instrumentation parts. So in such application we are using control walls, and the first scenario is to size safety wall is the basis is that the control wall failure or PRV failure. That means key we have set some certain parameters in control wall or PRV, its mechanism fail, or in control wall it opens fully open, that means ki 100% opening. What would be the flow rate and the pressure? So based on that, we have to size the safety wall for this case. Then the second scenario is thermal expansion due to hydraulic lock. In this case, as we all know, we have a common practice in industries that we transfer the raw materials from tank farm to the plant. It's having lengthy pipelines across the pipe rack, or the same scenario can happen any of the equipments as well, as which we use the utility as a cooling medium in that case. So the hydraulic lock means if we have supply utility in any of particular reactors and utility return wall is closed by any means, that means our flow is restricted, that means lock trapped in between, and due to exotherm generation inside the reaction or high temperature reaction material, the heat is transferred to the utility, and due to increase in temperature, the fluid inside the reactor jacket, or which is transferred from tank farm to plant or plant to tank farm, that got trapped in pipeline gets expanded in respect to the expansion coefficient of that particular material. Okay, Then third scenario is that decomposition or runaway reaction. As we know, we call it as runaway reaction or any particular reactions which display the acceleration or sudden change in rate of reactions under certain circumstances like utility failure or less agitation or charging of extra material or extra catalyst. So, and these are difficult or impossible to control. Such a reactions are called runaway reaction. And I would like to just give some of the example of runaway reactions like polymerization, nitration, hydrogenation, halogenation, sulfonation. These are the few type of reaction which most probably falls under the this runaway scenario. Okay, for this we have to size the safety wall based on its DTA or DSC. DTA is the differential thermal analysis method, or some industries using differential scanning calorimetry or reaction calorimetry to get its results. And DTA is the basically graphical representation of difference in temperature versus time. So next scenario is external fire case. Okay, in external fire case scenario, we all know that the fire hazards arises in a plant or in a tank farm, any part of plant. Okay, we have number of equipments or tanks which are filled with some organic, inorganic, and solvents like materials. Those are highly flammable or more volatile, that having the boiling point is low, that directly affects with the temperature. And in external fire case, that directly impacts on the rise in temperature of material, that directly uh, forms or increase the vapor pressure of liquids inside the equipments, that may be tank or reactor. Okay, and after certain time, the vapor pressure or that pressure built up inside the equipment goes beyond the design pressure. So, and there probable chances of rupture or uh, blast of that equipments. To avoid such a scenario, we have to size the safety wall considering the external fire case. And in external fire case, the relieving rate is calculated based on the wetted surface area. And we will discuss about each different scenario with the example in the upcoming series of safety wall sizing calculations. So as you know, we'll get the basic equations for the sizing of orifice, type of orifice selection, or what would be the orifice area for the safety wall. But it's little bit difficult to get the equation easily to calculate the relieving rate of the liquid or gases. So as per the API 521, I have attached a snapshot of equation which we used to calculate the required relieving rate, because unless and until we have relieving rate and the set pressure, we can't proceed for the safety wall sizing. Okay, so to calculate the required relieving rate, first we have to calculate the cubical expansion coefficient of the liquid. So here is the formula to calculate the expansion coefficient of particular fluids. I'll just explain one example to you. Suppose we are transferring xylene, toluene, or any of the solvent, acetic acid, from the tank farm to the plant, and it's having length in between 200 meters to 650, 600, whatever it may be. As you know, the tank farm, there is distance between tank farm and the plant. So based on that distance, the transfer of the liquid takes place at the room temperature usually. Okay, so we need to calculate cubical expansion coefficient. First we have density of that material. For acetic acid we have 1040 kg per meter cube, and initial temperature is 30 degrees Celsius or 30 to 35 degrees Celsius as a atmospheric temperature. And we need the secondary temperature and the density of that particular temperature. And thermal expansion is happened most of the cases due to the external temperature, or that may be due to during daytime due to sun rays or radiation energy, or in summer season you will face the expansion related topics more. Or so we have to consider 60 degrees Celsius max for this thermal expansion coefficient calculation, and based on that we have to check the density for that particular temperature, and with the help of this equation we'll get expansion coefficient, and with the help of expansion coefficient and other data we can calculate the required relieving rate using above equation, which I have stated in earlier slide. And in with the help of this equation, this can be available anywhere on, you can google it for the liquid as well as gas, or for steam application vapor liquid phase also. Okay, with the help of this equation we will get the what is the area required of the orifice, and based on that we have different type of orifices that we can call technically it as a designation type, like D, E, F, G, I, J. And for particular designation of orifice there is a certain orifice area as per the standards of safety wall sizing. Hope you got the some clarity about what are the different scenarios which are commonly used for the sizing of safety wall. And if you have any queries you can drop me a message or comment in a comment section, and we continue for the further sessions so that you can get the idea about how to calculate the safety wall sizing or relieving rate for the different scenarios in upcoming series. For now, thank you. Bye bye.